Morning, students. So today is day 4 and I'm going to present you part 4 of kinetic theory of gases and radiation. So this is the last part of this chapter. From tomorrow and onwards we are going to see numericals which are related to this chapter. Alright, so let's move towards the next slide, which is going to explain what we have learned yesterday, and then we are going to see what we are going to see today in this slide and in this part also. Okay, so let's move towards. Yes, what we have seen yesterday, we have seen Mayer's relation, then we have seen specific heat capacities, that is at constant volume as well as at constant pressure. We have seen specific heat capacities of diatomic molecule, monatomic molecule and polyatomic molecule too. Alright, and next we have seen conduction, convection and radiation. These are the three modes of transfer of heat. By using these three, heat can be transferred from one body to another. So these are the three modes and we have seen the difference between them. Then what we have seen? We have seen absorption, reflection and transmission. What is absorption? When any body is got incident by an heat radiation, suppose the amount of it energy is Q, then some amount of it will get absorbed through that body, some amount will get reflect and some amount will get transmit. So we have seen the relation between three of them, that is A plus R plus T is equal to 1, where A is coefficient of absorption, which is QA upon Q, R is coefficient of reflection and T is coefficient of transmission, which is QT upon Q. We have seen all of three of them. We have seen diatherminous substances and atherminous substances too. And we have seen many of the concepts which are related to coefficient of absorption, reflection and transmission. Let's move towards the next part, which is going to tell you about perfectly black body. We have seen something in short in the previous slide, what is perfectly black body, and in today's part we are going to see more details about this. Then we are going to see Fairy's black body. This is the black body which is being created by scientist whose name is Fairy. So the name is given after him, so it is Fairy's black body. Next is emission of it, that we are going to see, emissivity, that we are going to see in this part. Then theoretical proof of Kirchhoff's law of radiation. Kirchhoff's law of radiation is nothing but A is equal to E at constant temperature. What is meaning of that? Coefficient of absorption is equal to coefficient of emission, and we are going to prove that theoretically. Then spectral distribution of black body radiation. This spectral distribution, or we can say energy distribution of black body radiation, this gives us a next law, which is Venn displacement law. These two concepts are very related to each other. By doing this point you come to know about this point. So these are related to each other. And next is Stephen-Boltzmann law. This both scientists combinedly give a law, and that we are going to see. Some proof of it we are going to see also. So these are the points which we are going to learn today. So many points are there. So let's go quickly to the next slide, which is perfectly black body. Now these are the points which we should consider when we say it is a perfectly black body. We have seen what is black body. What is black body? In a relation of coefficient of absorption, coefficient of reflection and coefficient of transmission, the addition of three of them is 1, right? We have seen that yesterday. When we say R is equal to 0 and T is equal to 0, that means when reflection doesn't occur and even transmission doesn't occur, only absorption takes place for a body, and that body is known as perfectly black body, for which A is equal to 1. perfectly black body doesn't exist in the universe, but there is one example. Lamp black is the example in which 97% of the heat which is radiated on it, it gets absorbed, but 3% will get either reflect or transmit. So perfectly black body doesn't exist, but we try to make one black body which absorb almost 99% of it which is radiated on it. We'll move toward that part which is known as Ferris black body, but we'll see first perfect black body. These are some points which are related to that. First point is a body which absorbs the entire radiant energy incident on it is called ideal or perfectly black body. Okay, thus A is equal to 1. Then on what factors it depend? It depend either the surface of a body and nature of the body. Then lamp black or platinum black that absorb nearly 97% of incident radiation hit. So these points I have already told you this. Now good absorbers are always a good emitter and poor absorbers are poor emitters. What is the meaning of this? Good absorbers are always a good emitter. Consider one example. Suppose two bodies are there. One body is get polished and second body is painted with black, and same amount of energy is given to both of them, or both are at same temperature. What happens if energy is radiated on it, or suppose heat energy is given to both of them? The polished body will not totally absorb the energy which is incident on it, but the body which is been painted with black will absorb all the energy. But as it absorb all the energy, it will try to emit the energy. Alright, so what happens when it emits? The rate of emission of thermal radiation, when it is emitting energy, the rate of emission will be should equal to rate of absorption, because the amount which he is absorbing, he should emit in the same amount, so as to maintain the temperature. The amount of absorption should be amount of emission, both should be equal. So this gives the relation between temperature as well. So we are saying good absorbers are always good emitters and poor absorbers are poor emitters. Okay, so this is all about perfectly black body. Moving towards the next point, which is Fairy's black body. Yes. So this is the Fairy's black body. You can see the diagram. In diagram, what you can observe in diagram, it is a hollow sphere, all right, and in between, as it is a hollow, so this is the evacuated space between them, and outer part is polished with silver, okay, and inner part is polished with lamp black. Then there is one small aperture over there through which energy is going to radiate inside this body. There is one conical projection over there. It will allow the ray to travel throughout the black body or throughout the body, and it will ensure that the ray traveling along the axis of the aperture is not incident normally, because if the incident radiation will be normal to this, it will go back in the same direction also. So as it will go back, so it will not be a perfectly black body, right? Perfectly black body means what? It should absorb all the energy, all the radiant heat which is incident on it. So for that purpose, the inner surface is being coated with lamp black. Alright. So this is doubled walled. First wall is been polished with silver, and the inner wall is polished or coated with lamp black, and there is a conical projection which assures that the heat which is radiated on it will not be normal. So the emission or the incident radiation which is coming inside it on this conical projection, so it will be roaming inside it, and it will try to cover a many number of reflection inside it, but all the wave and all the reflection will be get absorbed, and very negligible amount will be come outside. But we are considering not no one amount of zero amount of radiation will coming out, and that is been ensured by this conical projection. The conical projection is doing the role of what? Due to that, radiation is not going back, it is not reflecting. So this is the role of conical projection. All right, so this will behave like a fairy's black body, and it is called as fairy's black body. I hope you all got that. It is very easy, and it asks for 3 marks in board exams. It is usually asked question, so you have to do this with using of diagram. If the long answer type question, when it is not asked in long type, it may be asked in to draw a diagram of fairy's black body. So you have to do practice for this diagram, and also you have to go through this. Okay, so this is all about fairy's black body, which is man-made black body. Okay, so let's move towards. Now we are going to see emission of heat radiation. What is emission? In the first slide we said that the amount of heat which is absorbed, it will get emit. What is meaning of emission? It is throwing out of the body. Heat is throwing out. So let's see what happens in emission. All the bodies at all temperature above 0 K. What is 0 K? It is absolute temperature. Radiate thermal energy at the same time they absorb radiation. That's what I told you. All the bodies which are having temperature above absolute 0 temperature, they will try to radiate, or they will try to emit heat radiation at the same time they absorb. So that's why it is a common thing that when the absorption should be equal to emission so as to maintain the temperature. So these are many things which are related to temperature itself. So let's move towards the next point. What it tells us, the amount of thermal radiation emitted per unit time depend on the nature of emitting surface, its area and its temperature. Now why is it given like it depends on the nature of emitting surface and its area and its temperature? It is because we said that the amount of energy which is incident on any surface, that surface defines either it is a black body or it is a good reflector. If it is polished with silver, it will get reflect all the radiant heat. If it is black body, then it will get absorbed. So that's why it is said that the amount of thermal radiation emitted, it will be depend on the nature. Alright, and its area also, and its temperature. Alright, moving towards another point. For a body, the absorbed radiation, as it is being a energy, so it increases what? It will increase kinetic energy of the constituent atom oscillating about their mean position. If we consider any object, the molecules within inside it will try to move, because the energy is nothing but the thermal energy given to it, and as energy increases, then kinetic energy, that means the motion between them, will goes on increases, and they will try to move from their mean position, and they will try to oscillate. But in yesterday lecture we have seen that the average translational kinetic energy determines what? It determines the temperature. We have seen the relation between them by using equation of pressure, that was E by N is equal to 2 by 3 T, and there is one constant. Alright, so this is the average translational energy determines the temperature of the body. Now let's see what is thermal equilibrium. What is thermal equilibrium? Thermal means it is obviously related to heat. Heat means temperature and equilibrium means something should be equal. Now what should be equal? Thermal equilibrium. Temperature should be equal. But which temperature should be equal? Let's see. When the rate of absorption of radiation, same as the rate of emission of radiation, the temperature of body remains constant and the body is said to be thermal equilibrium with the surroundings. We'll take a short example by which you are going to come to know what is thermal equilibrium. If we take a cup of hot coffee and we put it on a table, all right, what happens after 1 hour to that tea? Suppose the temperature, initially the temperature was 60 degree. When I put that cup of tea on a table, the temperature of that is 60 degree. After 1 hour, what happens to it? Within 1 hour, the temperature will goes on decreases and it decreases up to the temperature of the surrounding. So there is a thermal transmission, there is a transfer of heat energy between surrounding and in the cup of a tea which is having temperature higher than the surroundings. So the temperature will decrease up to the room temperature. So that is nothing but both the bodies are in thermal equilibrium. So this is nothing but about thermal equilibrium. Next, we'll see what is this. As we have seen emission, we are going to see something about emissive power. So amount of heat radiated by body depends on, first is temperature, obviously. Second one, we have seen nature of the body. Third is surface area of a body and time duration, obviously. Amount of heat radiation depends on temperature, nature of body, surface area, time duration. So let's see the definition of emissive power. So emissive power is amount of heat radiated, Q. Amount of heat radiated, which is Q, is directly proportional to the surface area and time duration. So we are going to consider the whole term as Q by AT. Okay, radiant heat is directly proportional to A as well as directly proportional to T. So Q by AT gives you a term which is called R, and this R is nothing but emissive power or radiant power, R of a body at given temperature T. So this is nothing but emissive power or radiant power. Okay, so this is nothing but Q upon AT, where Q is radiant heat, A is area and T is time duration for which body emits radiation. So we are going to see the dimension of it and SI unit. So dimension by using this is L0 M1 T minus 3. Okay, and SI unit is joule, as Q is heat, so it is joule. Area meter square, T will be in seconds, so joule per meter square per second, or this. Okay, so this is all about emissive power. So let's move towards the next point, which is coefficient of emission or emissivity. Similar to coefficient of absorption, coefficient of reflection, coefficient of transmission, we are going to see coefficient of emission. So let's move towards it. The coefficient of emission of a given surface is, that means E, we are going to say that is at E. The coefficient of emission of a given surface is nothing but the ratio of emissive power of a body to emissive power of black body. So it is R divided by RB. It is very easy. What is emissivity? As we have seen, what is absorptivity? It is QA upon Q. But in this case, we have to consider emission power. So it is R upon RB. Okay, so E is R by RB. For perfectly black body, what is E? E will be 1. So R is equal to RB at that time. So E will be 1. And whereas for perfectly reflector, when all the energy get reflected, it will be 0. So emissivity will be 0. Now we are going to see the Kirchhoff's law of heat radiation and its theoretical proof. Now let's see what is Kirchhoff's law of radiation first. It is nothing but A is equal to E in a simpler way. It is nothing but A is equal to E, where A is what? Coefficient of absorption and E is coefficient of emission. Okay, so this happens at thermal equilibrium condition. That means temperature is same, at which coefficient of absorptivity it becomes equal to coefficient of emission, or it is called emissivity. Absorptivity is equal to emissivity is nothing but Kirchhoff's law of radiation, and theoretically we are going to prove that. Let's see how we are going to prove. We are going to consider two bodies which is enclosed in a geometrical shape enclosure in which temperature is same. Alright, in thermal equilibrium we are going to put two bodies in which one is ordinary and second is black body. That means consider A as ordinary and B as black body. Okay, both are same in shape. Okay, and they are at thermal equilibrium. That means same temperature as that of the enclosure in which they are put. Then let R emissive power of A, RB emissive power of black body. A is coefficient of absorption of A. Q is quantity of radiant heat. QA will be quantity of radiant heat which is absorbed by body A. Then according to the definition of absorption, coefficient of absorption, QA is equal to AQ. We already have seen this. QA is equal to AQ. As the temperature of body A and black body B remains the same, both will emit what? They both must emit the same amount of energy. Alright, so the emissive power or the quantity of radiant heat, the amount of heat which is radiated by the ordinary body should be quantity of heat radiated by body A. Is it right? The amount of heat which is radiated should be equal to amount of heat emitted, as the temperature is same. So we are getting AQ, amount of heat radiated, AQ is equal to emitted. So it is R, because R is amount of heat emitted, right, by A itself. For perfectly black body, what will be Q? Q will be RB in a simpler way, and A is equal to R upon RB. How is it so? As Q is RB, then what will be A over here? This QB will be here. So A will be R upon RB. So R by, but by the definition of emissivity, R by RB is E. So we are getting A is equal to E. Very, very simple, and it comes for 3 marks in board exams. So you have to do this. First, what we are going to consider, in an enclosure, two bodies are there which are at thermal equilibrium. A body is ordinary body, body B is black body, and then we are going to consider the terms which are related to them, such as R is emissive power, RB is emissive power of black body, Q is heat is radiated, A is coefficient of absorption. That all terms you are going to write, and then, as you know, the quantity of heat radiated will be QA, that will be A into Q. As the temperature is same, then amount of heat which is radiated by A will gives you amount of emission, which is by A itself. So AQ is equal to what? What is amount of emission by A? It is R itself. So we are getting AQ is equal to R. But for perfectly black body that we are going to consider inside it, this, there is a question of two body, not only one. So we have to consider the second body, which is black body B. So for perfectly black body, Q is equal to RB. Amount of it, total amount of it will be RB. That means emissive. All the radiant heat will get absorbed. No? So that is nothing but RB. So by putting the value of Q as RB over here, you are getting A as R upon RB. But R by RB is what? Emissivity, which is E. Therefore, you are getting Kirchhoff's law, which is A is equal to E. 1, 2, 3, 4, 5 steps are there inside this proof. And this is very easy. Okay. So let's move towards the next, which is spectral distribution of black body radiation. Okay, spectral meaning we are going to see the energy distribution of black body. Alright, so let's see. Observe this graph first. At y-axis it is radiant power or emissive power, you can say, and here it is wavelength, Newton meter. Wavelength of the range of 0, 500, 1000, 15,000, 2000, 1500, sorry, 2000, 2500 and 3000. And these are number of temperature is written over here, and here is written as lambda max. Now what is this? Let's see. As we said that, and as we discussed that black body radiates. Firstly, the energy which is radiated on this black body will absorb all the energy. As it absorb, it will try to emit energy. As it emit energy, that will be having number of radiation. It will radiate. So it will radiate number of waves inside a surrounding to the surrounding. So wavelength will be differ as it continuously radiating energy. Alright, so wavelength, this will differ. See, number of wavelengths are there and it is differing. Now some scientists have discovered or have put a theory forward of spectral distribution. They consider that if we increase the temperature of black body, what happens to the wavelength and what happens to the emissive power or what happens to the radiant power, which is being explained by this theory and which is being explained by this graph. So this 3000K, 4000K, 5000K and 5500K, that is nothing but a black body of different temperature. A body which is having temperature, black body having temperature 3000 Kelvin, it will radiate number of wavelengths, it will radiate number of waves inside or to the surrounding, and it is having number of wavelengths. So what happens? So this curve you can observe. This is the curve showing different wavelength it is giving at temperature 3000 Kelvin, and the energy at 500 is this much, energy at 1000 is this much, at 15008 this, at 2000 it is this. So the energy got distributed throughout the wavelength and throughout this. So the section which is below the wave, below this graph, is nothing but radiant energy or emissive energy or radiant power. So this is nothing but spectral distribution. So the energy got distributed. I am not saying it is equally distributed. I am just saying it is get distributed. So let's see what is the relation between temperature and that energy. So moving towards, as we increase the temperature of black body, what happens to this curve? See, number of wavelength will be there. Energy is distributed in this manner. Alright. So by considering the first, Let us consider the first. What is the highest radiant power to this graph? It will be, suppose, something here between 500 and 1000. And if we increase the temperature, it is shifted towards left. See, at here, at this point, radiant power is more. It is shifting towards left. By considering this, let's increase the temperature of black body up to 5000 Kelvin. As we increase up to 5000, again the peak will goes on increases and then it goes on decreases. See, at 5000 the radiant power is this, 5000 wavelength. At 1000 it is here, and in between them it is here, and it is maximum in between 5000 and 500 and 1000. So again it got shifted towards left. So as we increase the temperature, the radiant power is shifting towards left. The peak is shifting towards left. That means wavelength is goes on decreases, right? So when we are getting maximum, let's see, when we increase the temperature up to 5500 Kelvin, by increasing the temperature up to that point, you are getting peak like this. The peak is again shifting towards left. That means the wavelength is going to shift in this manner. So as we have seen in light section, different colors are due to different wavelength of the wave. So the wavelength goes on changing. That means we are getting different colors. So when we consider when two bodies, when we consider to one of them, when we increase the temperature of one body, it may get convert into red, suppose iron. Alright, so when we increase the temperature of that, it will convert into a red color. That is due to this phenomena. Alright, and one of the example to which it will get converted into white. So this is the another phenomena. So different colors of that are due to different wavelength, and some of them are in visible region. So this is the visible region. And lambda max is nothing but lambda, that means wavelength at which radiant power is maximum. Lambda max is not maximum wavelength, it is wavelength at which radiant power is maximum. So by using this graph, what you can observe, as we increase the temperature of black body, the peak of the graph is shifting towards left. Alright, and wavelength is goes on decreases. As we increase the temperature, wavelength goes on decreases. So this is nothing but Wien's law. Why is it displacement written over here? As the peak is displaces. This is Wien displacement law. Before that, these are the point which we have right now we have discussed. These are the point that explains all the graph that I have already explained to you, right? So I am not going to read all this point, just go through it. I have already told you all this point by explaining the graph. Alright, so let's move towards the next, which is Wien displacement law. As we have seen by the diagram, as t goes on increases, lambda goes on increases, so they are inversely proportional to each other. So lambda max is inversely proportional to t. So lambda max is equal to b upon t, where b is called as Wien's constant and its value is 2.897 into 10 raised to minus 3 meter per Kelvin. Now where this law is being used, it is used to determine the temperature of distant stars, sun and moon, etc. How? We know the distance and we know the temperature of that planet, so we can find out as b Wind's constant is constant, so we know the value of that, and T is the temperature of that planet. So we know both the terms, so you can calculate lambda max. Alright, so let's move to, or vice versa, if you know lambda max we can calculate T as B is known to us. So this is wind displacement law. Next and the last point of this chapter is Stephen-Boltzmann law of radiation. Now, what is Stephen-Boltzmann law? This law has been stated by two of the scientists. So that's why it is named after that. That it's Stephen and Boltzmann. These are the two scientists who invented this law. That is nothing but R is proportional to T raised to 4. What is meaning of that? Emission is completely dependent on the temperature, but it is as dependent, so it is the fourth power of temperature dependence is. So R is proportional to fourth power of temperature. So this is nothing but Stephen-Boltzmann law. And to remove this, they multiply the constant term which is sigma, which is given by Stephen. So sigma is known as Stephen constant, whose value is given over here and whose dimension is this. Okay. Now, there is something related to Stephen-Boltzmann law of radiation. See, if we consider Q is the amount of radiated, R is nothing but Q upon AT. We have seen that. Q upon AT. So, Q upon AT is equal to T raised to 4. Alright. So, for which body is not a black body, the energy radiated per unit area, per unit time, still proportional to fourth power of the temperature, but less than that of the black body. Yes, obviously. If it is an ordinary body, it will be proportional to T raised to 4, but it will be lesser as compared to black body. Alright. So let us consider for ordinary black body, there will be some emission, right? So R is equal to E sigma T raised to 4 for ordinary. And for black body, no amount will be radiated, no amount will be emitted. So it will be simply R is equal to sigma T raised to 4. And for ordinary, it will be E sigma T raised to 4. Energy radiated per unit time, per unit area will be sigma T raised to 4. At absolute temperature, it will be sigma T0 raised to 4. What will be net energy absorbed? So energy absorbed from the surrounding per unit area per unit time, as we have seen this. Therefore, the net loss of energy will be sigma T raised to 4 minus sigma T0 raised to 4. By taking out sigma, we are getting T raised to 4 minus T0 raised to 4. Now, what happens to the ordinary body? For ordinary body, we have to multiply it by term E, because there will be some emission. So it will be E sigma T raised to 4 minus T0 raised to 4. Now, what happens if T0 is greater than T? So we have to consider the second equation, which is E sigma T0 raised to 4 minus T raised to 4 in case of T less than T0, in case of T less than T0, because we cannot consider it in negative sign, right? So we just shuffle both the terms. So we are getting this. So this is net gain in thermal energy of the body per unit area per unit time. So this is all about today's lecture, and this is what we have seen today. What points we have covered? Perfectly black body, Fairy's black body, emission, theoretical proof of Kirchhoff's law, which is A is equal to E, and we have seen spectral distribution of black body radiation, and according to that we have seen wind displacement law, and the last point which we have just covered, which is Stephen-Boltzmann law. Okay, so thank you so much for watching all the video, and here I am declaring that kinetic theory of gases and radiation is finished. From tomorrow onwards we are going to see numerical, and we'll see a short revision of that, all the chapter. Okay, so thank you so much. And I have posted a link of a class test over there. To mark your presentee, you have to attend that class test. Yesterday only about 70 students have attended, and I am marked attendance of them only. Rest of the students are absent in my side. So to mark your presentee, you have to attend that test quickly after watching this video. Okay, thank you so much.